Hey guys, Miss Peterson here, and welcome to AP Chemistry Lecture 8-1, all about the pH scale. We're going to be talking about pH and pOH, the strengths of acids and bases, and a little bit about the water dissociation constant, which is Kw. You can find more information in Chapter 16 of your Brown the May textbook, and this is AP Chemistry Topics 8.1, 8.2, and 8.6. We'll also be doing some practice on this in class. So, first off, let's review, because it's been a while since we talked about acid-base reactions way back in Unit 4. So the definition of an acid, there are two definitions. The Arrhenius definition, a substance that when dissolves increases the concentration of H+, versus bases increases the concentration of OH-. Now, this is kind of a limiting definition because it only really applies to aqueous solutions, or solutions where water is involved. So we have the other definition, the Bronsted-Lowry definition, which is that acids are proton donors and bases are proton acceptors. Now, a little note, remember a hydrogen atom is just one proton and one electron. So when we say proton, you can also think of that as an H+. Okay, and we will be using those two, proton and H+, interchangeably throughout this unit. The pH range for acids is 0 to 7, where bases is 7 to 14, and we have those ion concentrations, where acids have a greater concentration of H+, and bases have a greater concentration of OH-. Neutral is defined as when the concentration of H+ equals the concentration of OH-. Okay, and that happens at pH 7 for water at 25 degrees Celsius, but know that it is dependent on the temperature. So if we look at this example, acid-base reaction, okay, we have the highlighted H+ in the HCl acid that is donated, reacting with that H+, you see how that H gets donated to the base which accepts it in the forward reaction. Now this is a strong acid, so we wouldn't see much of the reverse reaction, but if we did, we could see it that way, okay? And you might remember this language, since the HCl is the one with the proton, and then over here that Cl- could accept a proton, it is the acid's conjugate base. Conjugate base to that HCl acid, where this base, the NH3, has a conjugate acid, which is the NH4+. So we have HCl and NH4+ as our bases in this reaction, and NH3 and Cl- as our bases in this reaction. Okay, cool. Okay, cool. So that brings us to conjugate acid-base pairs. Basically, you're just looking for the species that differ by only a proton. So we have HNO3 as an acid. If it removes that H+, it becomes NO-, the conjugate base. Okay, where we have water here acting as a base, accepting that proton to form H3O+. Water's conjugate acid. Now, water can act as an acid or a base. So we see in this reaction, we have ammonia, NH3, acting as a base by accepting the proton from water, acting as an acid. And we see that water's conjugate base is OH-, and ammonia's conjugate acid with that H+ is NH4. Now, this differs by proton is so common that we often can just represent acids using H, the proton, plus A, the acid. For example, the NO3, or in this one, it would be the HOH, okay? So then A- would be the conjugate base or the deprotonated form, okay? So if we're looking for the conjugate base, here's a list of acids. Acids are proton donors, so their conjugate base is remove one H+. Therefore, remember that it's a plus, so the H goes away and we're left with ClO4-. Okay, Here, the H goes away. We have HS minus. Okay, conservation of charge. We have to consider that. We could even write the whole reaction. Okay, we have HClO4 plus H2O. If it's acting as an acid, it's donating that proton to form ClO4 minus and H3O plus. Okay, so we see that pair relationship. pH4 plus becomes pH3 without the positive charge, and HCO3 becomes H2CO3. Okay, cool? Okay, cool. Now, for conjugate acids, okay, we're given bases. Okay, these are bases. If we're looking for its conjugate acid, we have to add an H plus. Okay, so the Cn minus becomes HCN. The SO4 2 minus becomes HSO4 minus. Okay, H2O conjugate acid, it becomes H3O plus, and HCO3, okay, add another H plus, and we have H2CO3. Hey, did you guys realize I messed up? I just realized I messed up. It can't be the conjugate base and the conjugate acid. I added an H here instead of removing it. It should be CO3 2 minus. Okay, cool. Okay, cool. Let's go ahead and go on to the next section, which is about the strengths of acids and bases. So a strong acid is an acid that completely transfers its protons to water, or completely disassociates, completely ionizes. Basically, we don't have any HA left. It's all H plus and A minus. Now, the conjugate base of a strong acid, well, the reverse reaction doesn't really happen. So it's not really a base. It's basically a very bad base. For example, if you look up here, HCl, a strong acid's base is Cl minus. And it's just not a very good base. It's not very good at accepting protons, because then it would become HCl and it would just break apart again. So our strong acids that we do need to memorize are these 7: hydrochloric, hydrobromic, hydroiodic, perchloric, sulfuric, and nitric. And there's no trick there. I'm sorry. You just have to memorize them. Okay. Now, a weak acid, most acids are weak acids. They partially disassociate in solution. And the conjugate base of a weak acid is a weak base. Okay. And you can kind of see that relationship over here. If we have a strong acid, it's going to be a very poor base. Weak acids become weak bases. And if we had a strong base, it's not going to be a very good acid. So they're inversely related, okay, from those conjugate acid-base pairs. As the acidity goes up, the strength of its conjugate base goes down. Okay? But why? Why are some bases stronger than others? For that, we have to look to the molecular arrangement. So here's an example where we have hypochlorous, chlorous, chloric, and perchloric acid. Now, perchloric acid and chloric acids are both categorized as strong acids. Okay? Now, why though? Why do you think perchloric acid is such a stronger acid than hypochlorous? Well, it goes way back to our unit on molecular properties and structure, okay, and electronegativity. Now, we know that oxygen is really electronegative, or is pretty electronegative, and so is chlorine. So if we look at this molecule, there's going to be a partial negative charge here and a partial positive charge here. And that is true for the hypochloric acid. It's polar, so it can lose that hydrogen. Now that is even more true for the perchloric acid. This is going to have a strong negative charge and a strong positive. This is going to be a superpolar molecule. all of that electron density is going to be over here on the perchlorate ion rather than on that H+. So because of that difference in charge, it makes that H+ a lot easier to remove. If it's easier to remove that hydrogen ion, then it's going to be a stronger acid. Okay, so it's all down to electronegativity. Okay, perchloric is more polar, so the H+ is easier to remove. Okay. The electronegativity differences in the molecule should be more specific. So because the perchloric is so much more polar, that H+ is going to have a much stronger positive charge on it and thus be easier to remove. Okay, cool. Okay, cool. Now, another way that we'll do this is we will talk about our K values. That's coming up in our next lecture. But another way to look at it is to just look at that general reaction, okay? We have HA and H2O, H3O+, and A-. We have this as, I'll label this as an acid. This one is its conjugate base. And then this one's here acting as a base, and the H3O+ is its conjugate acid, okay? Now, if this acid is stronger than this acid, okay, then it's going to drive the reaction. The forward reaction is going to be favored because it is a stronger acid, okay? If it was a strong acid, we know it would only exist over here. If HA is stronger, it's going to drive it that way, meaning our K value is going to be greater than 1. It's going to be product favored. Where if H3O+ is a stronger acid, then the reverse reaction is going to be favored, and the equilibrium would lie on the reactant side and have an equilibrium constant less than 1. We could also look at this in terms of the bases. If H2O was a stronger base than H-, then the forward reaction would be favored, okay? It would accept the protons to create there. Where if A- was the stronger base, then it would accept the protons and become HA, and thus the reverse reaction would be favored. Okay? Okay, cool. So now, based on the strengths of our acids and bases, we're going to rank them in terms of the smallest to largest K value. So first, let's just go through and identify all of our acids. Okay, I'm going to highlight our acids in, we'll do pink because it's the closest to red I got. So we have the acetic acid that donates a proton to the HS, forming H2S. So H2S in the reverse loses a proton. It is an acid. In here we have the NH4 that loses the proton. It is the proton donor, and so is HF. Okay. Now note, these are not the conjugate acid-base pairs. These are the acids involved in the reaction. So this is an acid, this is its conjugate base. This is a base, this is its conjugate acid. Okay? And then our last one. Now, let's do some analysis. First off, what I hope jumps out at you is this HCl. HCl, we know, is a strong acid. Okay, that means it dissociates completely. This equilibrium is going to lie only on the reactant side because that HCl is such a strong acid. So we know for this one, the K value is going to be much, much less than 1 because it's going to be so reactant favored, okay? Because of that reverse reaction. Now for this one, we have HF and NH4+. Which of those is a stronger acid? Let's check. So here is HF, and then the other one was NH4+, which is right here. HF is the stronger acid. So it is going to be the one driving this reaction. It is more likely to donate a proton than the NH4. So the reverse reaction will be favored, and thus we know that K is going to be less than 1. Okay. Now for this one, we have acetic acid, CH3COOH, and H2S. Which of those is the stronger acid? Well, if we go up here, so erase our ones from last time, here's our acetic acid, and here is the H2S. So H3, or acetic acid, is going to drive this reaction. The forward reaction is going to be favored because it's more likely to donate a proton. So here we know that K is going to be greater than 1. So now to relate it to the K values, okay, the smallest K will be this one. This one would have the largest K because it's the only one with a K greater than 1, and this one would be the middle. Okay, cool. Okay, cool. Now let's talk about water. We know water is special, okay? You haven't made it this far in chemistry without knowing that water is special. And just like its polarity makes it special, another thing that makes pure water special is its autoionization, okay? A sample of pure water isn't all H2O. A very small portion of it turns into H plus and OH minus. Now, it's such a small portion that the concentration of water doesn't change in it. It's going to be relatively constant, but the H plus and OH minus ions can. And so when we write their equilibrium expression, it is the concentration of H3O plus times the concentration of OH minus. Now, you guys might notice something that some of the reactant kind of changed here. Okay, H plus and H3O plus are used interchangeably. Okay. So we'll go ahead. I like using H plus, so we're going to go ahead and fix it there. Okay, but know that H plus and OH minus are used interchangeably in chemistry. It's just whether it's bonded to a water or not. I think H3O plus is slightly more accurate. Okay, that is what happens more often. But H plus is shorter, so we do tend to use it. So we have that equilibrium expression. Now this is a constant. It is always going to be equal to 1 times 10 to the negative 14. Therefore, when we add acids or bases, they act as common ions, okay? They will shift the equilibrium, but keep this value the same, which allows us to find out all sorts of things about the solution. Now, if this is true, okay, Kw is 1 times 10 to the negative 14, what would be the concentration of hydrogen ions and hydroxide ions? Well, remember our rice tables? Guess what? They're going to be here a lot longer. If we have some change in X, this will be X, and this will be X. So we can set that up as X times X, or X squared, equals 1.0 times 10 to the negative 14, meaning that X, which is the concentration of H plus, and the concentration of OH minus, because it's a 1-to-1 ratio, is 1 times 10 to the negative 7 molar in a sample of pure water at 25 degrees Celsius. Now, that's a small number, okay? H pluses are always going to be small numbers, but, you know, scientists don't really like small numbers. We do, they're fine, but if we can make it easier, we do. So we'll normally express hydrogen ion concentrations in terms of pH, where P means the negative log of, okay? Now, most often, this is going to be pH. pH equals the negative log of the H plus concentration, which for water would, in pure water, of 1 times 10 to the negative 7. Okay. Now, you guys might remember logs, okay? A log means 10 to what power is 1 times 10 to the negative 7? Well, 10 to what power is 10 to the negative 7? Negative 7. And then we have the negative of that number. So the pH of pure water is 7, okay? And that means that the pOH of pure water, it's going to be the same formula, is also going to be 7. And just so that we're being specific, this is at 25 degrees Celsius. Okay. Now, mathematically, these ideas have a lot of power, okay? Both this one and this one. So much so that we're able to develop all of the equations around them, okay? So let me start with the basic ones that are on your equation sheet. On your equation sheet, you do have Kw as being H plus times OH minus and equal to 1.0 times 10 to the negative 14, okay? You also have the pH equals negative log of the H plus concentration, and pOH equals negative log of the OH minus concentration, okay? But these allow you to do some other cool things. First, we can undo them, okay? I'm going to do the ones in green that are not on your equation sheet. So to undo a log, you do 10 to the 10 to that power. So 10 to the negative pH is going to equal the concentration of H plus. And thus it's the same for pOH. Okay. And because these concentrations always multiply to 10 to the negative 14, pH plus pOH will always be 14. Okay? And these equations allow us to calculate lots of different things. Let's go ahead and put them into practice. Starting with the pH of vinegar, which is a solution of acetic acid, is 2.8. What is the concentration of hydrogen ions? So concentration of H plus equals 10 to the negative pH, 10 to the negative 2.8. Now, we don't usually leave negative signs in exponents, so we have to plug that into our calculator to get our value, which is 1.58, so 1.6 times 10 to the negative 3 molar. Okay. Now, we can do the reverse. What is the pH of a 0.4 molar solution of hydrochloric acid? Hydrochloric acid, we know that this is a strong acid. So the concentration of HCl will equal the concentration of H plus ions because it donates all of them. So pH equals negative log of 0.45 molar, which gives us 0.35. What is the difference in pH between a solution of 2 molar and 1 molar solution of nitric acid? Now, your gut instinct might be to be like, oh, well, if the concentration doubles, the pH is going to double. Let's see if that is true. Okay, or you might think it'll times by 2. Let's find out. So HNO plus is also a strong acid. So we can just use its concentration as the concentration of H plus. So for the pH of the 1 molar solution, we get a pH of, am I doing the negative log of 1? Yes. Okay. I said pH of 0. 10 to what power is 1? Yep, that would be 0. Where the pH of a 2 molar solution would be negative 0.3. Okay, these are very concentrated solutions of a strong acid. So we're kind of seeing that the pH scale does go beneath 14 and over beneath the 0 and over 14. This is a true story. It does not mean that there's anything wrong with your calculations. It's just a very strong acid. Okay. Now, a solution of NaOH has a pH of 10.5. What is its molarity? Okay, here's where we got to start using some relationships. NaOH, that is an alkaline metal, and OH, so this is going to be a strong base. So the concentration of OH minus will equal the concentration of NaOH. And there's a couple different ways we could find that. We could find our concentration of H plus from the pH and use this relationship, or we can do 14 minus to find the POH and do it that way. And I think that's a little easier, so I'm going to do it that way. So our POH would be 14 minus 10.5. I'm going to rewrite that so you guys can actually see it, which gives us a POH of 2.5, 3.5. Okay, I can math. So our concentration of OH minus, which will equal our concentration of NaOH, will be 10 to the negative 3.5, which is 3.2 times 10 to the negative 4 molar. And you could always check it by doing the other method. 10 to the negative 10.5 would be 3.2 times 10 to the negative 11. And if we do 1 times 10 to the negative 14, divided by that, we get 3.2 times 10 to the negative 4. And that's the basics of pH. Okay, cool? Okay, cool.